Hello students, good afternoon. How are you all? Am I visible and audible? If I'm visible and audible to you guys, just give me a thumbs up or let me know the answer in the chat box. Yes, fine. So nice to take class for you all after a long period of time. And so today we are going to discuss the thermochemistry part of thermodynamics lesson. Okay. So yesterday, I think Vivek sir have covered the thermodynamics part with you guys. Am I right? Is that the thing? Thermodynamics he has covered, I think. Yes? Am I right, students? Yes or no? Or he has covered the thermochemistry also. Okay. So yeah, so today we are going to continue with that lesson, that is thermochemistry. So here the topics that we are going to cover in this session are the thermochemical equation, Hess law, thermochemistry, spontaneity, Gibbs free energy, and equilibrium constant. Okay. So coming to the thermochemical equation, so coming to enthalpy of, already we have discussed this, just this is the recap of it. Okay. So it is the energy change accompanying a reaction is called as enthalpy of reaction. Okay, for example, we are having a reactant and reactants are giving the products. Okay, NAB are the reactant, CD are the products. Now, if I want to find out the enthalpy of the reaction, enthalpy means delta H, right? Change in enthalpy. So delta HR means it is enthalpy of the reaction. So to find out that, what I have to do? I have to subtract this enthalpy of product and the enthalpy of the reactant. But it's summation of sum of enthalpy. I can also write like this: summation of enthalpy of the products minus summation of the enthalpy of the reactant. Okay, so this will give us the delta HR naught. This will give the enthalpy of the entire reaction. Got it? So this is the formula that you have to note down here. And coming to the next topic, that is the standard enthalpy of reaction. So what is that? Enthalpy of reaction, standard enthalpy of reaction. So it is the enthalpy change for a reaction when all the substances are in standard state. I'll show you the standard state of some elements in the next slide. So here the standard enthalpy is denoted by this, by putting this 0 at the top in the superscript. Okay. So delta HR naught is called as standard enthalpy of reaction. Conditions are 298 Kelvin and 1 bar pressure. Okay. Now, coming to the standard enthalpy of formation. So, enthalpy change for the formation of 1 mole of compound from elements in their most stable state is called as standard enthalpy of formation. So, 1 mole of the substance has to form from its constituent elements in their standard state. So, what are the standard state of the sum of the elements? So, for carbon, the standard state is graphite, and for bromine, it is liquid. And for oxygen, the standard form is gas form. And for iodine, it is solid. For nitrogen, it is gas. For phosphorus, we have white phosphorus, red phosphorus, black phosphorus. But the standard form of phosphorus is red phosphorus. Okay. And for mercury, it is liquid. And for sulfur, we have two different types of sulfur, but chromic sulfur is the standard form of the sulfur. Okay. So when 1 mole of the compound is formed from its constituent elements in their standard state, then the energy change accompanying that type of system is called as standard enthalpy of formation. Okay. So any doubt from this? Shall we discuss this with some more examples? Do any of you have any doubt from the students? Jain V. Ramnagar students? Shall I move on to the next slide? Yes or no? Okay. So here you see calcium oxide is reacting with carbon dioxide and it is producing calcium carbonate, and standard enthalpy of formation for this reaction is given as minus 178.3 kilojoule per mole. And here you see, it is not the standard enthalpy of formation because we have calcium, carbon, and oxygen in calcium carbonate. The standard form of calcium is calcium. For carbon, it is graphite form. Okay. And for oxygen, the standard form is O2 in gaseous state. So calcium, carbon, and oxygen. These three elements should be there in the reactant side. But instead of this, we have calcium oxide, which is a compound, and also we have carbon dioxide. So they are the compounds. They are some of the compounds. The 1 mole of calcium carbonate is formed, but it has not been formed from its constituent elements. That is calcium carbonate oxide. Okay. Instead of this, it has formed from calcium oxide and carbon dioxide. So even though we write delta HR not for this reaction, this value doesn't denote the standard enthalpy of formation of this reaction. Okay, clear? The calcium carbonate is not formed from constituent element, but it has been formed from compound like calcium oxide and carbon dioxide. Is this clear? Any doubt from this? Shall we move on to the next example? Are you all ready? Yes, good. So coming to the next example, and here you see H2 is reacting with Br2 to moles of HBr. Here you see 2 moles of HBr is formed. So what is the standard form of hydrogen? H2, and for Br, Br2 in liquid form, and here hydrogen in gaseous form. These are the constituent elements of the given thing. Yeah, the reactants are the constituent elements, but 1 mole of the compound only has to form, but 2 moles has been formed here. So this value doesn't denote or represent the standard enthalpy of formation. Okay, so this is how you have to find out the correct answer from this type of equations. Okay, 1 mole of the compound should form, and it has to be formed from its constituent elements. It has to be formed from its constituent elements. Okay, so with this, standard enthalpy of formation is getting over, and next we are moving on to Hess law. So Hess law is very important, but it is very easy also. Thus, it states that regardless of the multiple stage or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. So, for example, A is giving B. The enthalpy change accompanying this process is called as delta H. Okay. Now, if A takes the other path, that is, if A is coming to C, then C is getting converted to D, then D is getting converted to B. So, this is the second path. Okay. This is path number 1, straight path, and this is path number 2. Okay. Now, this particular delta H will be equal to delta H1, delta H2, and delta H3. So, if we sum up all the enthalpy change here for path 2, we will get the same answer that we get from delta H, that is from path 1. Okay, this is Hess's law. So we can have multiple steps. We can have 2-step, 3-step, 4-step, in number of steps, but the total enthalpy change for the reaction is sum of all the small steps. Okay, so this is Hess law. Got it? Then coming to the next point, next topic is standard enthalpy of combustion, denoted by delta HC naught. It is delta HC naught. Okay. So enthalpy change when 1 mole of the substance is completely burnt in presence of sufficient supply of oxygen. Combustion is nothing but heating a compound in presence of oxygen, right? So combustion means enough amount of oxygen, enough supply of oxygen is given to that particular compound and it is burnt. That is called as combustion. Now here, 1 mole of the substance has to undergo this combustion process. Then only we call that a standard enthalpy of combustion. Okay, and the conditions are reactants and product should be in standard state. Pressure should be 1 atmospheric pressure and temperature should be 290 Kelvin because they are the standard forms of pressure and temperature. Okay. Now let's see an example. So C4H10. C4H10 is nothing but butane. Okay. So butane is reacting with 6.5 moles of oxygen to give 4 moles of carbon dioxide and 5 moles of water. Okay. So here we have only 1 mole of the substance. When only 1 butane we have, no. So 1 mole of the substance is burnt with the sufficient supply of oxygen. Got it? To produce if carbon dioxide and water is coming out, we can tell that the given compound has undergone complete combustion. Okay. If incomplete combustion occurs, then we would not get carbon dioxide and water. Instead of carbon dioxide, we will get carbon black or carbon monoxide. So that type of poisonous gas will be coming out. Okay, the compound undergoes incomplete combustion. So means it doesn't have sufficient supply of oxygen. So that's why it is happening. But here, butane is taking sufficient supply of oxygen to produce carbon dioxide and water. Okay, so delta HC naught can be written. And here you can notice that the value is in negative because the process is exothermic in nature. Because the process is exothermic in nature, and that's why we have negative symbol over there. Is it okay? Standard enthalpy of combustion is clear to all of you? Yes? Yes or no? The standard enthalpy of combustion clear to all of you guys? Yes. So the next term that we are going to discuss is standard enthalpy of atomization. It is delta H A naught. So it is the enthalpy change for the conversion of 1 mole of any substance into individual gaseous atom. So here also we are going to have 1 mole of the substance, and that 1 mole is getting converted to going to get converted to individual gaseous atom. Okay, and here the product should be in gaseous state and the process is endothermic. Okay, unlike the previous case, this is endothermic in nature. So the delta H value will be positive. Here you can see. So we have a hydrogen molecule. Okay, H2 is a gas and this molecule. So this is the bond between two hydrogen. And if I break this bond, energy is required, no? So that energy is nothing but enthalpy of atomization. That is called as enthalpy of atomization. Just give me a second, I'll be back. Okay, sorry for the interruption. So we have the hydrogen molecule here and the energy is required. Energy is required to break this bond. Okay, energy is required to break this bond, and here hydrogen molecule is getting converted to two hydrogen atom. Okay, so and the enthalpy change accompanying here is positive because energy is required. It is an energy absorption process, and that's why we call this as endothermic process, and it is denoted by the positive sign. Okay, and the product should be in gaseous phase. No, so here you see the hydrogen atoms are in gas phase. And for the other thing, sodium in solid form is getting converted to gaseous form. So 1 mole of the sodium is getting converted to gaseous sodium. So here this is also called as enthalpy of atomization, but solid getting converted to gas is also called as sublimation. No, solid getting converted to gas is also called as sublimation. So here both are equal. Okay. So this is standard enthalpy of atomization. The formation of atoms, formation of gaseous atoms, individual gaseous atoms from one mole of any substance. That substance may be molecule, that substance may be an atom, okay, solid atom, it can be anything, but one mole of that reactant has to form the gaseous product, okay, gaseous atoms. So that is this. Then coming to the next term, that is bond enthalpy. It is denoted by delta H bond knot, and it is energy required to break the bond. Energy observed in breaking of one mole bond in gaseous phase is called as bond enthalpy. So here we have a chlorine molecule. So chlorine molecule is present in gas phase, and there is a bond between these two chlorine atom. Single bond, sigma bond is there. Now, if I want to break this bond, I have to give some energy, right? So that energy is called as bond energy. Okay, bond enthalpy or bond energy, both are same only, more or less. And if I break this bond, what happens? The two chlorine atoms, they are separated. Okay, so here one mole of this chlorine is absorbing some energy and the bonds are broken down to form the gaseous chlorine atoms. Okay, this is bond energy. So here 242 kilojoule. Here also it is positive because it is an energy absorption process. And here both the reactant and product should be in gas phase. In the previous case, what we have seen here, in the reactant we have solid form and then the product side we have gaseous form. No, but in case of bond enthalpy, both reactant and product should be in gaseous state. So that is the difference between these two. Got it? Now, the enthalpy of reaction in terms of bond energies can be calculated using this formula. Suppose if you want to find out delta HR naught by using bond energy value, just do reactant minus product. Reactant minus product. So all the bond energy values will be given to you in the examination. So who are the reactants here? CH4 and Cl2 are the reactants. No. So the bond energy for these two will be given to you in the question. So what you have to do, just you have to sum up those two and put it in the left side and minus product bond energy values. That's all. Okay, and all substance should be in gaseous state. Clear for all? If some other substance is there in liquid form or solid form, suppose if HCl is there in liquid form in this case, means you should not take the bond energy of that HCl. You have to put 0 in that case. Okay, only the gaseous state bond energy values has to be used to find out the delta HR naught. That is standard enthalpy of reaction in terms of bond energy. Is it okay, students? Any doubt from this? Shall we move on to the next topic? Are you all ready? Or if you're having any doubt, you can put it in the chat box. Okay. Okay, good. So the next topic is lattice energy and hydration enthalpy. So let us discuss what is lattice energy first, then we will move on to hydration enthalpy. Okay. So lattice energy. The energy required to break 1 mole of ionic compound in solid state to form free gaseous ions are called as lattice energy. So I'm taking a lattice, that is NaCl lattice. NaCl is present in solid form. Now this is present as 1 mole. Okay. So now I have to break this 1 mole of NaCl. So this is 1 mole of NaCl. NaCl is an ionic compound. You all know that it is present in solid state. Now, the energy required to break all the NaCl interaction in this lattice, that is called as lattice energy. So, if I break all the sodium chlorine interaction, all Cl minus and Na plus will be separated like this. No, so it is getting separated into gaseous cation and gaseous anion. So, they are the free gaseous cations and anions. Now, here bond breaking is occurring. We are breaking the bond here. So bond breaking is always endothermic in nature. And if the process is endothermic in nature, then value should be positive. It should be positive. Okay. You can write down and keep this. So the bond breaking process is always endothermic in nature. And all the endothermic system will have the positive delta H value. Okay. So if I'm breaking 1 mole of lattice, that is called as lattice energy. Clear? Now I will give you the difference between the energy absorption process and energy released process, that is exothermic and endothermic. Okay. So shall I move on to the next slide? If you want to note it down anything from this slide, you can note it down and let me know if you are done with it. Shall we see the next part? Shall we see the difference between endothermic and exothermic? Yes. Yes, students. JNV Ramnagar. Okay. So if energy is getting absorbed in a process, that is, we call that as 1 mole of compound will give positive gaseous ion. That is energy absorption process. If energy is released, when does an energy release? When gaseous ions give join together, when Cl minus and Na plus, if they both react together to form this NaCl, 1 mole of an ionic compound, in that case, bond is forming. So it is an energy released process. Okay. Here bonds are broken and here ionic bonds are formed. Here bonds are broken down. No, here you see. And here two bonds are formed between these two compounds. And if a bond breaking process occurs, delta H value will be positive. And if bond is forming, delta H value will be negative. So this is an endothermic process, and the energy released process is called as an exothermic process. Is that okay? You can take down the tabular column for your better understanding. So this is about lattice energy. So the next part that we have to discuss is hydration enthalpy. Shall we move on to hydration enthalpy? Yes? Yes? Or no? Are you all okay with lattice energy? No? Okay, okay. Give me a thumbs up if you are done with it. If you are done with lattice energy, the tabular column, give me a thumbs up. You have given thumbs down. Okay, okay. I'm waiting. I'm waiting. I'm waiting. Let me know if you are done with it. Till that, I will wait. Yes. Okay, good, good. So the next is hydration enthalpy. It is denoted by delta H hydration naught. So the enthalpy change when 1 mole of a substance or ion is completely hydrated by water, then we call that as hydration enthalpy. So here you see sodium cation in gaseous form is reacting with X moles of water. It's reacting with X moles of water to produce Na plus cation in aqueous form. So this is the gaseous sodium, and this sodium is surrounded by X amount of water molecule. So in water we have two ends. No? Water is a polar molecule. Okay, it is a polar molecule. We have H2O like this, and here oxygen is the negative end and hydrogen is the positive end. Hydrogen is the positive end. No, so we have plus minus part like this. So the negative part, that is the oxygen part of the water molecule, interacts with the sodium cation because only the negative attracts the positive, right? So the negative part, negative side of this water molecule, you see, it is interacting with the gaseous cation, that is sodium, and now it is no more the gaseous sodium in the product side, it is the aqueous cation. It is the aqueous sodium, or it is called as hydrated sodium. Hydrated sodium ion or aqueous sodium ion. So here you see, so there is a formation of bond. There is a formation of bond between the gaseous cation and the anion of this water molecule. So bond formation is occurring. Bond formation is occurring. So bond formation is nothing but exothermic process because energy will be released if a bond is being formed. So delta H value will be negative. Bond formation is an energy released process. Okay, so that's why the value is given in terms of minus here. Delta H hydration for this ion is minus 406 kilojoule per mole. Okay, so this is hydration enthalpy. You need to understand the concept and you have to memorize the definition with one example. And all these things you have to do by understanding. Okay, don't just memorize, understand each and everything. Only a very, very minute difference will be there between one term and the other term. Okay, so just have a look on it, study thoroughly, don't get confused. Clear? So this is up to hydration enthalpy. The next is enthalpy of solution. So shall I move on to the enthalpy of solution? Are you all ready? Enthalpy of solution. Shall we move on to the enthalpy of solution? Yes. So the enthalpy of solution can be calculated by adding the lattice enthalpy and hydration enthalpy. Okay. And the solubility of ionic compound like NaCl or some other ionic compound if we take, and if we want to find out the solubility, we can use lattice energy and hydration energy value. So lattice energy, if it increases, solubility decreases. So solubility is inversely proportional to lattice energy. And the solubility increases with increase in hydration enthalpy. So solubility is directly proportional to hydration enthalpy. So here it is inversely proportional and here it is directly proportional. So this is what you have to keep in mind. We can find out the solubility of an ionic compound from lattice energy as well as hydration energy. The lattice energy, if in the examination, if they give you two compounds, how will you find out which compound is more soluble? Just by seeing the value of lattice energy. If the lattice energy is more, solubility is very less. The lattice energy is very less, solubility is more. So that is the meaning for inversely proportional and directly proportional, right? So accordingly, you can use this relation and you can find out the answer accordingly. Okay. So the next topic is entropy. The next topic is entropy versus spontaneity. So now we are going to see what is spontaneity and then we will try to connect this with entropy. Okay. Now what is a spontaneous process? The process which does not need any help of external agency is called as spontaneous process. So examples you see, I'm having an object A that is a hot object and also I'm having object B and that is cold. And if I bring these two blocks together, what happens? Heat will flow from hotter object to colder object, right? So I just brought the two blocks together, that's all. Automatically heat is transferring from block A to block B. So it doesn't need any external agency every time, okay, for the flow of this heat from A to B. So just only one time I have just brought them close to each other. Automatically heat is transferring. So that is called a spontaneous. It doesn't need any help every time. Okay. So these processes are called as spontaneous process. And also one more example here. You see water is flowing from, water flows down the hill. So it just coming down. It is just coming down from the top. It doesn't need any external agency to come from top to bottom. Okay, so these reactions are called as spontaneous reactions or spontaneous process and it cannot be reversed. It cannot be reversed. Suppose if you separate these two blocks from each other, heat cannot flow from the B object to A object, right? It cannot be reversed. Got it? The heat which is there in object B, it cannot go to object A if I separate this back. So it cannot be reversed. Spontaneous reaction cannot be reversed. This is an important point you have to keep in mind. Okay. Now, with this concept, I would like to go with the next slide. So now every system, if you take, they try to reduce its energy to gain the stability. So we all know this relation before. When we were discussing chemical bonding lessons, I have told you, no, stability is inversely proportional to energy. If an object or if a system is having very less energy, then only we can say that particular system is more stable in nature. If the energy of the species is very high, if the energy of the species is very high, then that is not stable. You can take a person also. If a person is in very high energy state, then it means that that person is not stable, no? He is unstable. In the same way, if the energy is very less, stability is more. So energy and stability are inversely proportional to each other. And this is the fact. And every system tries to do this. Every system tries to keep them in its lowest energy in order to attain the stability. Okay. So keep this also in mind. And with this, we will move on to entropy. So entropy is denoted by the letter S. So it is the measure of degree of disorderness or randomness in a system. So entropy means disorderness or randomness. That's all. And here you see, we have three cases in the picture. The first one is solid. I'm taking second one as liquid. And I'm taking third one as a gas. And we all know that solids will have the more ordered arrangement. So orderly arrangement will be can be observed in case of solid. So orderedness is more, means entropy is very less, because entropy is disorderedness. Clear? And here we have medium entropy because particles are a little bit separated from each other. There is no ordered arrangement over there in case of liquid. And then coming to solid, all the gas molecules are randomly moving here and there inside a container or some other room. Okay. So here disorderedness is more. If the disorderedness is more, entropy is more. Okay. Disorderedness more means entropy is more. Entropy is directly proportional to disorderedness. Clear? So the entropy of a gas is more compared to entropy of a liquid compared to entropy of the solid. Clear? Direct entropy cannot be measured. So delta, yes, change in entropy can be measured. So let me put delta. Okay. So this is an important relation you should know. Now we will see some more points about this entropy. So some of the properties of entropy are, first of all, it is a state function. What is a state function? The property or the function which depends only on the initial state and final state is called a state function. Okay. So if I know S1 and S2, I can find out delta S. So it is a state function. And also it is an extensive property. Means if I change the size of the system, the value will also change. That is called as extensive property. We might have studied the definition for extensive property in thermodynamics. That is the first half of this lesson. Okay. So the properties whose value changes on changing the size of the system are called as extensive property. So entropy is also an example for extensive property. Means if we change the size of the system, the entropy also changes. Okay. And this relation just now I have told you, gases are having the highest entropy, then liquid and solid. And if we want to find out the standard change in entropy of the reaction, then we have to do product minus reactant. What we have to do? Product minus reactant concept we have. Clear? So these are the 4 important points that you have to keep in mind regarding this entropy. Okay. And now coming to the next part. So entropy, it can be in terms of, it can be represented by using 2 variables. One is using heat and the other one is using temperature. So it both are giving one formula, that is delta S is equal to Q by T. Reversible. This is for reversible. Okay. Heat by temperature. And delta S means large change. Ts means small change. So if I'm putting ds, I have to put dq here divided by t. Okay. So this is one of the very important formula which will be used for solving the numericals from this part. So just to have a note on it. And if you want to find out the change in entropy of the universe, then we have to do change in entropy of the system plus change in entropy of the surrounding. So that will give the change in entropy of the universe. System plus surrounding will give the universe. That's all. Okay. Then entropy versus spontaneity, which is nothing but the second law of thermodynamics. So it you see here, we have gas A and we have gas B. Now I have mixed both the gases A and B. And here if you see randomness, since the volume is more here, the randomness, the movement of this the randomly arrangement of the gas molecules, that is more. Randomness is more. So the entropy of the product is more compared to the reactant. Entropy increases if I mix these two gases together. Okay. So that is nothing but the second law of thermodynamics. Now, entropy of the universe increases. Entropy of the universe increases, and it will be greater than zero. Delta S will be greater than zero. Okay, and this is a formula which we have already studied now. And for reversible process, it is equal to zero, and for irreversible process, it is greater than zero. Very important. For reversible, it is equal to 0, and for irreversible process, it is greater than 0. Clear? So these are the points you have to keep in mind regarding the spontaneity or entropy. Okay? So with this, the second law of thermodynamics is also getting over with the entropy concept. Then the next topic is Gibbs free energy. Shall I move on to the next topic, students? Shall I move on to Gibbs free energy? Yes? Yes or no? Shall I go with the Gibbs free energy? Yes. No? Okay, okay. Okay, I'm waiting. I'm waiting for you. Tell me once you are completed. Previous slide you want? Yeah. Okay. Thank you. Okay. Good, good. The next topic is Gibbs free energy. So Gibbs free energy is denoted by the letter G, and it is also a property of a system. Okay, it is a state function, depends only on initial and final state, and then it is an extensive property, means the value changes on changing the size or quantity. And if I have to find out delta G naught of reaction, then I have to do product minus reactant. Okay, product minus. Just read carefully where we have to do product minus reactant and where we have to do reactant minus product. Okay, so you should not get confused there. This is very easy. Only if we apply the formula correctly. Okay, if we are doing the other way around, it will fetch us the wrong answer. So you have to study the formulas very carefully. And G is also having one relation with the H and Ts. G is equal to H minus Ts. Okay, that is actually G cannot be measured, only delta G can be measured. So delta G will be equal to delta H minus temperature of the system remains constant only. So it is minus T delta S. Delta H minus T delta S. Okay, this is the formula, very important formula. And using this formula, we are going to see some more information. Just write it down. Write the properties of Gibbs free energy. We have 4 property and 1 formula in this slide. Just note it down first. Shall I move on to the next slide? We will see one tabular column here using this delta G. Just the very important tabular column. Shall I move on to that, students? Have you all completed? Okay. Now here if you see, so this was the formula I was talking about. Delta G is equal to delta H minus T delta S. And if delta G is less than 0, then the process is spontaneous. If it is equal to 0, system is in equilibrium. If it is greater than 0, it is spontaneous. So always remember that delta G should be negative or it should be less than 0. Then only that particular process is spontaneous. If we are having positive value for delta G, then we can close our eyes and simply say that it is a non-spontaneous process. But if we have equal to 0, it is equilibrium. Okay. So this is the very important tabular column. And also we have one more tabular column. So that I will show you. It is there in your book also. That is also very important. So here is that. So if delta G is coming out to be positive, just now we have seen that the process is non-spontaneous. If it is negative, it is spontaneous. And for the last, we have two cases. If this delta H is negative, if this delta H is negative, and if T delta S is positive, then for plus, if delta G will come out to be, if it is coming out to be positive at a high temperature, it is non-spontaneous. And for low temperature, it is spontaneous, means only at low temperature, delta G value is negative. Only at low temperature, delta G is negative. At high temperature, delta G is positive if delta H is negative over here. Okay. Now, do the other way around. If delta H is positive and T delta S is negative, then only at very high temperature, it is spontaneous. And at low temperature, delta G is having positive value. So it is non-spontaneous in nature. It is non-spontaneous in nature. So how I am finding out this? If a process is spontaneous, then delta G value should be negative. Delta G value should be negative. So all these goes like this. Clear? Clear, students? It is there in your book also. You can go through that. That tabular column is very important. Okay. Then coming to the next topic, that is Gibbs free energy and equilibrium constant. Equilibrium constant is denoted by KEQ. It is denoted by KEQ. So we have a reaction, A moles of A giving B moles of B. And delta GR can be written like this for this reaction. And instead of this reaction quotient Q, so all these reaction quotient, equilibrium constant, we have studied in chemical equilibrium lesson, no? That same thing. So equilibrium constant or reaction quotient, they are nothing but the product of product concentration divided by the product of the reactants concentration raised to their stoichiometric coefficient. So P is the product, A is the reactant, and the small a we are the stoichiometric coefficient. So always we have to write the product in the numerator divided by the reactant in the denominator. Okay. Now at equilibrium, delta GR will be equal to 0. And this Q can be written as KEQ. This KEQ is called as equilibrium constant. This is called as equilibrium constant. Now substitute these two values in this equation. So instead of, in place of delta GR, we will have 0. In place of Q, we will have KEQ. Okay. Just rearrange this. You will get this formula. And if you convert this LN into log, what you have to do? You have to multiply this by 2.303 number. So that is what is being done here. And at last, we have arrived at this particular formula in which delta G R naught is equal to minus 2.303 into RT into log of KEQ, which is very, very, very important. Okay. So with this, thermochemistry part of this lesson is getting over. Okay. So now we are left with few more minutes. If you are having any doubt, you can ask me. I will give you 15 to 30 seconds for doubt. And if there is no doubt, we can solve few questions, very few previous year's questions of JEE and NEET. And then we will wind up the today's session. And in tomorrow's session, we can discuss some other lesson. I think we can discuss redox reactions lesson in tomorrow's class. I mean, then in the next class, tomorrow is a holiday, no? So in the next session, we can discuss redox reaction. Okay, are you all okay for that? So shall I go with some previous year's questions of thermochemistry? Are you all ready? Yes or no? Yes. Good. So the first question is here. Consider the following reaction. What is the enthalpy change for decomposition of 1 mole of water? So here you see hydrogen is reacting with oxygen to produce H2. But we are asked to find out the enthalpy change for decomposition of 1 mole. Decomposition means product is getting, H2O is breaking down into H2 and O2. Means H2O has to come to the reactant side. So let me reverse this equation. Just reverse this equation. If I reverse this, what I will get? 2H2O will give 2H2 plus O2. Okay, this is called as decomposition. When one molecule is breaking down into two or more, it is called as decomposition. And also we have one more thing. Decomposition of 1 mole of water. Here we have 2 moles of water, right? Yes, very good, students. Since we have 2 mole, we have to divide this whole equation by 2. If I divide this by 2, H2O will give H2 plus half O2, right? So this will be the desired equation, and the enthalpy change, delta H for this reaction will be, so since I have reversed this equation, the enthalpy delta HR naught for this reaction will be plus 483.64 kilojoule per mole. I have to change the sign since I have reversed it. Now, in the second step, I have divided this equation by 2, right? So what I have to do? What will be the delta HR naught for this reaction? That is the desired equation. So it will be 483.64 divided by 2. So this will give us 241.82 kilojoule per. Very good. You have got the answer. Very good, students. Good. So we will move on to one more question. The equilibrium concentration of the species in the reaction A plus B giving C plus D are 2, 3, 10 and 6 mole per liter respectively at 300 Kelvin. Now what is delta G naught for the reaction? And R value is also given. We have to find out delta G naught. How will you find out? Which equation you will use? The last formula which we have discussed now, that has to be used now. So delta G naught is equal to minus 2.303 into RT log of K. So this is the formula. Okay. So just substitute minus 2.303 into RT log of, what is KEQ? It is an equilibrium constant. Now how to write the equilibrium constant? It is equal to the product of product concentration divided by the product of reactants concentration. So I have to substitute this in place of this KEQ. Now concentrations of all the reactants and products are given, right? For C it is 10 and for D it is 6 mole per liter. For A it is 2 and for B it is 3. Now substitute and cancel out, simplify this. So 2 gets cancelled and log 10 value is equal to 1, and here minus 2.303, R value is given as 2 and the temperature is given as 300 Kelvin into 1. So this will give us minus 1381.80 calorie. Okay, delta G naught is equal to minus 1381.80 calorie. So which is the correct answer? Option B is coming out to be the correct answer for this question. Okay, clear? Any doubt from this? Shall we discuss one more question and then wind up the class, or shall I wind up the class? What do you guys say? So it's already 3:56. So you have to give a break and go for the next class, no? So I'll wind up the class here. One more you want? Okay, then we will do one more. Which question? Okay. For irreversible expansion of an ideal gas under isothermal condition, the correct option is irreversible expansion. irreversible expansion. Irreversible processes are always spontaneous. Irreversible processes are always spontaneous. So for all spontaneous process, delta S value, that is entropy value, will be greater than 0. So this is the condition. Okay. And what other information we have here? Isothermal. Isothermal means what? Temperature is constant. No, this is the one more information we have in the question. So we have delta U and delta S in the options. Delta S is not equal to 0 because it is greater than 0. So either option C or D should be the correct answer. Now we have to check with delta U. Yeah, we know one formula, right? Delta U is equal to NCV delta T. And since temperature is constant, the delta T goes to 0. So 0 into anything is 0. So delta U is coming out to be 0. So which is the correct answer? Option D. Very good. Very good. Option D is the correct answer for this question. Is this enough for you guys? Or one more? One more? Shall I stop? Okay. So I'll give one more question. That will be the last question for today's session. So here is the question to you. Very easy. Direct substitution. You don't need to multiply or do any calculations. Just find out the answer first. Hydrolysis of sucrose is given by the reaction and equilibrium constant is given. Equilibrium constant is given as 2 into 10 power 13. Actually, it is not 800, it is 300. Okay. And we have to find out delta G R naught. So what you will do, which equation we have to use? Delta G R naught is equal to minus RT. And in all the options you see, it is ln. Okay. So it is not given in terms of log, it is given in terms of ln. So it is ln into KEQ. If we convert this ln into log, we have to multiply by 2.303. But that is not required. Keep this as ln itself. Okay, substitute. So it will be equal to minus, what is the R value? It is the R value 8.314 kilojoule. Sorry, joule per mole per Kelvin. And what is the temperature? Temperature is 300 Kelvin. Okay, into ln. What is equilibrium constant? It is 2 into 10 power 13. So this is delta GR, direct substitution. So option D is the correct answer for this. Option D is the correct answer for this. Is this okay for all? Clear? Enough. Okay. So you guys are so enthusiastic and participating in a very good manner. I appreciate you all for this. Keep the spirit till the end and study accordingly. Okay. Good. All of you are doing great. JV Ramnagar students are doing great work. So solve more questions from this topic. Okay. And practice because it is a physical chemistry lesson. So you have to practice more number of questions. So we will meet up with the redox reaction lesson in the next class. Okay. Thank you so much for listening to today's lecture. Take care. Bye-bye. Thank you all. Thank you all.